The topic of the video is spherical polar coordinate system and Laplacian operator in this coordinate system. The position of a point in a three-dimensional space can be specified using the Cartesian coordinate system as shown in figure number 1, in which we have the origin O and x-axis, y-axis and z-axis, and the point is taken as P. Here we actually draw a straight line from origin O to that point P, and we consider the projections like onto z-axis PA, and the length OA is actually called as z component of that position vector OP, and we actually have a projection of that point P in xy plane, which is PB, and we also have this OB vector there, and the projection of this OB on x-axis, which is OC, is our x component, and the projection of this OB on y-axis, which will become our CB, is our y component. So we can actually write down the position vector OP as the components triad x, y, and z in a bracket like that. In this system, we can say that all points or any point in space can be actually on a corner of a rectangle with one of the corners as the origin. But the position of same kind of a point in the space can be specified using three other variables, which we may call r, theta, and phi, and say that this kind of system of specification is called a spherical polar coordinate system, in which r is actually the length of the vector OP, and theta is the angle made by OP with the z-axis, and then phi is the angle made by the OB vector with x-axis. And here this r can be actually changing from 0 to infinity, because we want to give labels for every point in the infinitely long universe. And the theta can be changing from 0 to pi radians, and then the phi can be changing from 0 to 2 pi. And in this system, all points or any point can be actually appearing as if it is on a sphere of a specific radius and with a specific angles theta and phi. If you want to relate these xyz components to r, theta, phi values, we can actually compare the figures number 1 and 2, and that's what we have done here. And in the triangle OPA, which is this OP and A, it's actually rectangle triangle here, because right angle triangle here, because here the angle is 90 degrees, and here if you consider the cosine theta, which is adjacent, which is OA or Z, divided by our hypotenuse, which is OP, which is R. So cos theta is equals to Z by R, or Z is equals to R cos theta. And in this triangle OP and B, which is this triangle, it's also a right angle triangle, because the angle between PB and OB is actually 90 degrees here. So in this triangle, if we again consider the cosine, of course here the angle is 90 minus theta, because the angle was, theta between here, so here the angle is 90 minus theta. So if you consider the cosine of the angle here, it will become cos 90 minus theta, and it is equals to the adjacent, which is OB now, and divided by hypotenuse, which is OP, which is R. So we get OB by R is equals to cosine 90 minus theta, which is sine theta, So we can say that OB is equals to r sine theta. And in the triangle OBC, which is this triangle here, and if you actually consider the cosine, of course the here the angle is phi here, and it's also a right angle triangle because the angle between OC and BC is 90 here. So here again, if you consider cosine of this angle phi, which is adjacent, which is OC or X, divided by your hypotenuse, which is OB. So OB was r sine theta from earlier equation, so we get x is equals to r sine theta into cos phi. And in the same triangle, if you consider sine phi, which is opposite, which is y here, or CB or y here, and divided by your hypotenuse, which is OB, so we get y is equals to r sine theta into sine phi. A small length change along the direction r can be written as dl sub r is equals to dr, and small length change dl sub theta along theta direction can be written as r d theta. That's because dl sub theta can be taken as pp prime here, and in this triangle OP and P prime, where we had this r as OP or OP prime, and then this d theta is actually kind of angle between OP and OP prime. And in this, if you actually consider sine of d theta, which is equals to your opposite dl sub theta divided by your hypotenuse, which is r here. So since this angle is very small, we can even say that sine d theta is equals to just d theta, and from here we can say that dl theta is equals to d theta into r. So that's why we get this r d theta here. And for the small length change along phi direction, which we can call dl sub phi, we get r sine theta into d phi. And that's because if you consider this triangle here, in which we already had this OB, this OB or OB prime is equals to r sine theta, and if d phi is a small angle here, then dl sub phi is this distance here. So in this triangle, if you again consider sine of d phi, which is equals to opposite dl sub phi divided by your hypotenuse, which could be either OB or OB prime, whose values are sine theta, then if you actually say that this angle is very small, so your sine of d phi is equals to just d phi. So if you actually kind of reverse that equation, we get dl sub phi is equals to r sine theta into d phi, as here. Laplacian operator in Cartesian coordinate system is defined as dou square by dou x square plus dou square by dou y square plus dou square by dou z square. And if you want to actually kind of transform this into spherical polar coordinates counterpart, then we should be using this kind of definitions for dou by dou x, which is equals to d by dou r into dou r by dou x plus this kind of term. But if you do this kind of thing, the mathematics will get very lengthy. But there is actually a kind of a shortcut which is actually given in Griffith's book for electrodynamics, and that's actually we have to memorize this table, in which we have this first column as a system of coordinates, which could be either Cartesian or spherical, and then we have this UVW, which can be XYZ in Cartesian and r theta phi in spherical polar coordinates, and then FGH values, which are 1 1 1 for Cartesian, and then 1 r and r sine theta for spherical, and this del square of some kind of quantity A is equals to 1 over FGH and in the square bracket we have dou by dou u of gh over f into dou a by dou u plus etc. I mean plus similar kind of terms like this. And if you actually substitute the relevant values, for example, for Cartesian coordinate system, we'll be getting this quantity as the dou square by dou x square of a plus dou square by dou y square of a plus dou square by dou z square of a. And for spherical polar coordinates, if you substitute the relevant terms, we get dou square of some quantity a is equals to this expression here. And this is Laplacian operator in spherical polar coordinate system. That's it in this video. Thanks for watching.